Welcome to you all. We have in nuclear astrophysics Professor V.M. Datar with us to throw some light on the importance of neutrino oscillations and the neutrino detection, which plays a very vital role in understanding the various cosmological events. Professor Datar has been with BARC for the last almost 3 decades. He joined the training school in 1974 and officially started working with Professor C.V.K. Baba since 75. Since then, he has been taking very active role in various nuclear physics research programs, in addition to doing extensive work in neutrino mass oscillations also. I welcome Professor Datar to this program. Professor Datar, I would like to ask you, what is the importance of neutrino? Can you please tell us briefly why neutrino is important?
The neutrino is probably among the particles one of the least understood particles. It's a weakly interacting particle. It therefore can give us information about the interiors of stars, such as for instance the sun. Because of the weak interaction, it leads to a long mean free path, and in fact the neutrino can for instance travel through the earth with if it has MeV energy, then the probability of interaction is less than 10 to the minus 8 or so. So it can propagate in matter without almost without any attenuation. So it can give us information which originates from the source without any distortion. But on the other hand, of course, it interacts weakly, so there is some interaction, otherwise we couldn't have detected it. And potentially, for instance, this has the possibility to tell us even things like what is the interior of the earth. Can we X-ray, so to speak, the earth? We might be able to do that in future. The other thing is that the neutrino has already told us that we have to go beyond the so-called standard model of physics. The fact that the neutrinos possess mass implies that we have to go beyond the standard model. That already has come out. We might also learn more things about particle physics through the window of neutrinos. And of course, as you also mentioned, that neutrinos provide us with a window to the universe as well, a completely new window. Up to now, we have been looking at the universe through the electromagnetic spectrum, and for the first time in 1987, we detected neutrinos from a supernova explosion. So this has provided a new window, and in fact, part of that work has even received recognition in the form of a Nobel Prize.
If I understand correctly, originally it was proposed that neutrino is massless. Only to account for the missing angular momentum in the beta decay, it has been introduced. Now you say that neutrino has mass. There are quite a few papers claiming the mass to be somewhere around few keV, and then there were a paper saying that it is much less than a few electron volt. So can you please highlight?
Well, I mean, there were early experiments which showed that the neutrino has if it has a mass at all, and in particular the electron neutrino, that it has a mass of less than of the order of 40-50 electron volts. This was in the 60s and 70s. Limit was pushed further and further. In fact, around the 80s, there was a small ripple caused by one experimental group in Russia, which claimed to have observed a finite mass of the electron neutrino in the region of about of the order of 10 electron volts or so. It's repeated by other people with much more sensitivity and was proven to be not correct. And in fact, that limit was pushed in the electron neutrino case to about 2 electron volts, 2 electron volt by c squared. In the early 80s, again there was a small ripple caused by a group which was looking at, in fact Simpson from Canada, he was looking at the beta decay spectrum from tritium, and they claimed to have seen evidence for the emission of in 3% of these decays to a 17 keV neutrino. Yeah. That's a massive neutrino. Yeah. So immediately many people got going, and including us, CVK, myself and Amit Roy and so on, we got together and we did a quick experiment. And we showed that that is not possible. We pushed that limit that if there is a 17 keV neutrino, it is emitted less than 0.6% of the time. So we kind of ruled it out at that level. And then others pushed that limit even further, and I think that was taken by a further order of magnitude down. So we don't have any evidence for a 17 keV neutrino. So, the electron neutrino, of course, there are better experiments now which are trying to push this limit from 2 electron volt to 0.2 electron volt by c squared. That is the so called Catherine experiment.
Okay. So, if we understand and if we are able to detect these neutrinos, what sort of an information it will provide both on the composition of the sun as well as in the supernova? These are the two major sources of neutrinos. So, what type of information will it provide on the astrophysical?
Okay. As I said, historically the neutrinos were used to try to look for the nuclear reactions that go on in the sun. As happens in many areas of physics, there was a result that was not understood, and in fact that created the so called solar neutrino problem. And when the calculations towards solving this were refined, the so called standard solar models were refined, it turned out that this problem cannot be understood within the solar models. So, Bacall and others proposed that there is a particle physics solution, and in fact that particle physics solution was suggested already by Pontecorvo. But it was taken more seriously after Bacall improved his calculations to a point where it became imperative to call for a particle physics solution. And the Davis experiment therefore could be explained there. Then there were other experiments like other radiochemical experiments, the Galax experiments, the Snow experiment, the super Kamiokande and then the super Kamiokande results. All of them seem to indicate that there is this can be explained only in terms of neutrino oscillation. But of course, the definitive solution to that came through the Sudbury Neutrino Observatory, which actually showed that the shortfall in electron neutrino is made up by neutrinos in the muon and tau sector. So, they looked at the neutral currents, which is sensitive to electron, muon and tau type of neutrinos. They showed that that shortfall is made up in that when you add up these three contributions, neutral current sector, they all add up to what the solar. So, it is indeed a great triumph of the solar standard solar model that we got things right to of the order of 20% or so. With such a huge, massive star, so many processes going on that we got it right itself is a great achievement. Okay. Now, that being said, also subsequently there were other experiments which improved on the measurements of neutrinos, oscillation parameters in the mass matrix, they were the precision on that was improved. Now, it has probably come to a point where we can now go back and once this neutrino sector is cleaned up a bit, now we can go back and ask can we learn something about what is going on in the sun again by looking at neutrinos. So, I think that is the phase in which we are at present now. So, we can perhaps put constraints on some of these reaction rates and so forth by looking at neutrinos, which is fantastic.
One of the recent attempts is that LIGO. Can you tell something about the LIGO setup?
I am not, I think I am not an expert on that area, and I think probably Bala Iyer will be able to do that, do more justice to that, except that I just learned that, I have heard also at other times that the attempts to look at gravitational waves might, after that technology is mastered, provide us with a window to the universe in a completely different channel. Electromagnetic, maybe in the near future we will go in for neutrinos, to look at the universe through neutrinos, and maybe 20 years from now we will be looking at the skies through gravitational waves. Okay. So, that is, I think there is a great importance of LIGO and its upgrades and
advanced
versions of that.
And we also had some earlier experiments in Kolar gold mines.
Yes.
So, can you, what actually the status, can you briefly highlight what is the...
I was not personally involved in that, but my colleague Professor Nava Mandal, who is the spokesperson for the India based Neutrino Observatory project, he was involved in that, but I know of course roughly what is done there. In the Kolar gold fields, I think one of the they were looking at cosmic rays. Bhabha started this program of looking at cosmic rays. You go deeper and deeper and look at the muon flux. In the course of doing such measurements, the Indians hit upon a gold mine really in that sense, because they first discovered atmospheric neutrinos. Yes. So, the Indian team has a first to its credit they found evidence for atmospheric neutrinos. In fact, they beat Reines by not too large a distance, but by a couple of weeks. Reines of course is he found evidence for the electron neutrino. And this team, the TIFR and Osaka, and I think it was also a Durham team, they actually discovered evidence for atmospheric neutrinos. Subsequently, the TFR and Osaka, this group, Durham group, they went into looking for proton decay, because at around that time the grand unification theories had come up, and one of the most outstanding predictions of that was that protons should decay. So, they looked for they were the first in fact to set up quickly a detector underground in KGF. It was not a very massive detector, I think it was of the order of 100 or 150 tons detector, iron and proportional counters, but they could get it going very quickly. And the backgrounds at KGF, because they were the deepest mine in the world at that time, were very low, and so the only background that they had to fight with was the neutrino background. So, if the proton had decayed with the rates that were predicted by some of these theories at that time, with lifetimes of the order of 10 to the 29, 10 to the power of 30 years, then they should have seen these events. Unfortunately, they only had a couple of candidate events, but they could put upper bounds only, and nature did not oblige them. Otherwise, perhaps we would even have had a big discovery there. Of course, then the KGF mine being what it is, you cannot put very large size detectors there. So, other people who are building detectors could make much bigger ones, and the epitome of that is of course the super Kamiokande detector, which is the 50 kiloton water Cherenkov detector. So, these the other thing that happened was that in KGF the mines were becoming less economically viable. So, they had to close them down. So, I think around the 90s, around 1990, they started closing down these operations, and it became sort of financially difficult to maintain the mine just for an experiment of this kind. In any case, we couldn't have competed with the other groups worldwide in building bigger detectors at such a depth. So, we would have to come up to shallower depths, but then we lose the advantage of very low background. So, somehow that stopped, but if at that time somehow we had got a neutrino group together, we could have probably been in this field much earlier. But okay, in the absence of that, now we are trying to build up a group to set up a neutrino underground laboratory, an underground laboratory to do neutrino physics, and it's possible that soon we will get permission to do that in a site in Tamil Nadu.
This is the so-called Indian Neutrino Observatory.
That's right. That is the India-based neutrino observatory.
Project shape now it's coming up.
Yeah.
And what are the challenging topics which you would like to look at there?
There are some areas that are kind of bread and butter, which namely that we would like to see oscillations. We would like to see the rise and fall of these oscillations, and you can do that if you do neutrino measurements over a large range in zenith angle. That is possible, because you can look at all angles in principle, except for in the plane of the iron calorimeter plates. But the more exciting prospect would arise if one of the parameters in this neutrino matrix, the so-called θ13 parameter, if it is not too small, then we have the potential of making a discovery in that we can address the mass hierarchy problem. For instance, there are 3 leptonic eigenstates and there are 3 mass eigenstates. That is what we now believe based on the experiments that we have done, and not we have done, the community has done. And so, this it is known from the understanding of the solar neutrinos that M2 is greater than M1. But whether M3 is greater than M1, M2, by the way, the M3, M1, M2, that difference is very large. So, M3 could be either above M1, M2 or it could be below. And so, this is the so called normal hierarchy in which M1, M2, M3, or you could have an inverted hierarchy in which M3 is the lowest and M1, M2. So, we could address this problem. We could in fact make a discovery there if θ13 is small. So, that there is a small risk involved, but that is how it goes in physics. You can never tell how nature behaves. You can't order nature to behave the way we want it to.
So, if you considering the overall challenges that the neutrino physics poses to the scientific community, what is your advice to our youngsters who would like to pursue this, and what are the various avenues which are open to them, and what are the challenges which they should face?
I think if we get this underground laboratory going, there will be an exciting phase for the young people, because neutrino experiments, as you all know, are very long drawn out experiments. Even if we get permission tomorrow to build this laboratory, it will take at least another 8 years to get the whole of that project in place. That means to build the whole 50 kiloton iron calorimeter detector. 8, maybe it might overshoot to 10 years also. And then we will be making measurements. Of course, the measurements will start as soon as one of those modules is ready. But in order to take data, that will be another 5-6 years in the minimum. and it will go on for another 10 years. So, that is a kind of 15 to 20 year project. So, that is a good time for young people to enter this. Also, it will give them a hands-on experience of doing things, which is not very common these days in the area of particle physics, at least in nuclear physics, because most of the particle physics experiments are nowadays done abroad. So, it is only a very small component that you are making here and the taking abroad. And also many students are probably involved in the data analysis, and so they haven't even seen detectors. And so, this would be a very good experience for people to actually get into the thick of things and build detectors, test them and see them working in a laboratory. That will give them I think.
So, may I summarize by saying it will be a great opportunity for the youngsters
absolutely
to get hands-on experience.
Yes,
and if they have a feel for experiments,
yes,
it's the right opportunity and right time for them.
That's right. And this would be also a kind of frontline experiment.
Yes.
This is an experiment which other people are looking forward to.
Challenging.
We hope that we will be able to achieve that goal, and I think there is confidence all around that we are capable of it. Now, whether we deliver is, I hope we will be able to do it.
Can you also tell us something about the activities that you are currently involved in nuclear physics?
Okay. I am basically an experimental low energy nuclear physics, and my route to neutrino physics was through the experimental channel. There are experimental people needed for the neutrino project. However, my background in nuclear physics is mainly based on experiments that we have done at the Pelletron, the 14 MV Pelletron. It is a tandem accelerator which accelerates particles to typically about up to about 150 MeV. So, at Bombay there is such a Pelletron. There is another Pelletron run by the universities, UGC, through the Nuclear Science Center, now called the Inter-University Accelerator Center at Delhi, and also the Accelerator Center at VEC. So, I have done a few experiments in each of these places. I would, in the context of the astrophysics, nuclear astrophysics context, I would like to just mention that there is another very nice thing that happened a few years back, about maybe 7-8 years back, that there was a beryllium-7 radioactive ion beam facility which was developed in the country, and it was, I think, the best of its kind. Of course, I should say best of its kind, because there were other radioactive ion beam facilities in the world, and we were not the first in doing that. But I think with whatever facilities we had, one of the younger persons in the Nuclear Science Center had a nice idea of actually getting a beryllium-7 beam, and with the quality which is almost like the Pelletron beam quality. That means, it had a size of 2 to 3 millimeters, it had an angle divergence of about a degree, and that kind of quality did not exist anywhere in the world. I think even to this day, probably, except for now the ISOL facilities would give this kind of beam, but at that time this was, I think, a unique facility. So, we did one experiment there. It was a joint proposal by the person who developed this beam, a person called J.J. Das, and myself, and then we had a team of a few 7-8 people. We did this experiment to measure the S17, which is the proton plus beryllium-7 going to gamma plus boron-8. That is one of the key reactions which produces boron-8, and which in fact the boron-8 decay gives you the high energy part of the spectrum, which was important in the neutrino context, the solar neutrino problem, for instance. So, we made an indirect measurement of that. We made a measurement of the with using a beryllium-7 beam on a deuterium target. We measured the beryllium-7 DN cross section, and that is actually a strong process, but it tells you about the wave function of the proton in the boron-8. And so, once you know the wave function, then you can calculate the P gamma rate in beryllium-7. So, this was an indirect measurement, but the measurement was not so much important from the measurement of the S17 itself, although it did resolve some of the anomaly, not anomalies, I should say, the inconsistencies in the measurement. Some people were claiming that the indirect measurement does not give you the correct S17 factor. We showed that if you do a proper analysis, you measure also other data like elastic scattering data and so on, then we were consistent with the direct measurements, which is the direct beryllium-7 P gamma measurement. But more importantly, once we showed that this technique works, this technique could be used for the measurement of S factors, P gamma or alpha gamma factors of other beams, other radioactive beams, where the half-life of the radioactive species itself is very short. In the case of beryllium-7, the half-life is of the order of 50 days or so. So, you can actually make that target and then shoot a proton beam on it, and that decays only after 50 days, half of it becomes, half of decays only 50 days later. So, that is a nice target. but there are cases which where you have decays of the order of milliseconds or microseconds decays or seconds decays. Then you can't make that target and prepare it and put it as across the beam. So, in those cases such a indirect measurement would be useful. This is not a very precise measurement, but it gives you a first idea to the 10-15% level. So, I think that we showed, and I think since that was it was done in India, I think I am rather happy about it.
So, what was the challenging part of that experiment there?
The challenging part I think was done by this young colleague.
Okay.
He actually produced the 7 beryllium beam of that quality. That was the most important.
Okay.
The experiment was an offshoot of that, and of course, it required some care and so on, but we could do that. But I think the real credit goes to this young person.
How much is the current for that which you
No, this was done with very few particles. This was not done, this was done with about a few thousand particles per second.
So it's extremely
as opposed to typical stable beam experiments which are done with nanoampere currents, which means of the order of 10 to the 10 particles per second.
Enormously large.
So you have to have a detector with very good efficiency, and you have to do a careful job on that. But of course, in this case we could do it because the DN cross section is a strong, is mediated by the strong interaction.
Okay.
So there are, the cross section is of the order of tens of millibarns per steradian, as opposed to P gamma cross section.
That's quite high.
Which is very low. If you go to very sub-barrier energies, it could be as low as picobarns, whereas this one was millibarns.
Okay.
But the trick there is that you do this measurement which is quick and rough, and then you use that information to calculate the P gamma cross section.
Now, coming back to again neutrino problem, what is the international scenario on that? How are the various laboratories?
Now there are, several labs which have all got excited by this, the fact that the neutrinos tell us something beyond the standard model. So there are very many experiments, some very large scale experiments to look at these neutrino oscillations with much better precision. So one of the experiments which will start shortly is the so called T2K experiment, which shoots muon neutrinos at super Kamiokande detector. So they will look at these, and since they have a new machine in J Park which produces proton beams of rather large currents, so they can produce a very intense beam of nu mu, and they will look at this oscillation. They will look at both the flavor changing part as well as so they will look at so called survival. The part that the nu mu survives to remain nu mu, or that it oscillates into a nu e. So they will look at the appearance. So they will do both appearance and disappearance experiments. That is one. But there are also other experiments, like not directly to do with neutrino oscillations, namely the so called neutrino-less double beta decay experiments. So they are also the large number of groups which are attempting that. There is one experiment which has claimed to have observed already neutrino-less double beta decay in 76 germanium using germanium detectors, which are very high resolution detectors, and not only that, they have used enriched 76 germanium detectors with some 86% enrichment, and they have the first evidence. Of course, there is some people doubt that result. Nevertheless, that has excited many people, and there are at least about more than half a dozen, maybe half a dozen to a dozen experiments or planned projects. The closest is so called QRChino, which is now graduating into a QOR project, which is a cryogenic bolometer experiment on tellurium 130. So they have just reached the sensitivity of the germanium 76 experiment. Of course, they don't find any evidence for that yet, but that could be also because of differences in nuclear matrix elements which play a role here. So, but they will improve that sensitivity by about an order of magnitude at least, and they will then be able to address this issue. On a small way, we have also started some R&D towards making a neutrino-less double beta decay detector at the Tata Institute. It is also a collaboration between Tata Institute, Kharagpur IIT, BRC and so on, a few other institutes. And we hope to look for the first phase. Of course, we can only go step by step. We will try to build a small tin cryogenic bolometer. If we succeed in doing that, then we would like to build a bigger one and then take it to perhaps this underground laboratory that we are building for the neutrino observatory.
So, in summary, we can say that both within India and outside, there are very many challenging opportunities for the physicists youngsters who want to continue neutrino physics.
Yes, absolutely.
Am I right in saying that?
That's right, absolutely.
And I am sure that you will help in all possible ways the youngsters get the...
Oh yeah, I mean not only me, I mean there are many other people
sure.
who will also be most willing to help. We need young people and we need people with motivation, and I think there are great opportunities.
Thank you, Vivek, for your excellent introduction to the field.